Sorry, apologize. We will talk, first thing we're going to talk about tonight is spatial analysis using GIS. The things that we're going to talk about this evening and even into early April are really at the heart of GIS. We looked at mapping techniques, ways you can get data, remote sensing, and so on. But we looked at types of data, vectors, points, lines, polygons, that. But analysis is where really GIS provides the biggest opportunity to bang for your buck. This is what GIS does at its heart. It answers the questions of what, when, where, and why, searching for patterns and so on. And a big part of this, we'll need to think about layers again. I'm sure you've seen this from working in the labs. And this is a review from a slide. The first or second week of class, we had this slide. I pasted it in here just to review the concept that GIS data is separated into layers. And we analyze the relationships between these layers. And here's a conceptual screenshot of that, and here's a data frame from our map showing an example of different layers. In ArcGIS, and you'll do this, we won't talk about this much here because you'll work on it in lab. You do a lot of analysis and geoprocessing in the Arc toolbox. It's one example of many types of GIS analysis can be performed. If you have it in lab, you'll go through and you'll see there's hundreds of different analyses you can perform here. Since we cover these in the lab and there's no time, we're not going to go through them in that detail, but just be aware of our toolbox. I'm sure you use that in several labs, and you'll continue to do so. Some of the types of analysis that we'll talk about near the end of tonight are commands that you would find in our toolbox. So to some degree, this lecture is kind of a mixed bag or potpourri of different analyses, where we'll have one or two slides about different types of analyses. And the first one, I think we talked about a little bit last week, conflation. Conflation is combining the best features of two data sets into one. So usually this is done in conjunction with streets. So if you have let's say you have a very accurate street, here's all the bends in the pavement, but no information about it. You have another street, you have another GIS data set that represents the same street in a different layer. It's not as accurate, but suppose it has more detailed information. It has house numbers, road name, and so on. Conflation is an analysis that takes the best of both worlds. Best of both worlds is kind of a good layman's way to describe conflation. In conflation, you would take the good attributes on this street layer and run analysis to assign those streets to the other street layer that's more spatially accurate. And usually this actually is done with streets. And I think I did briefly touch on this last Tuesday, just at the end of class. It's not without risks. Well, the NFT did this about 15 years ago, and they caused a problem because the streets in Buffalo that are densely packed were shifted by more than one. So in other words, if this is layer number 1, you have Delaware, Franklin, and Elmwood. I have these backwards. I'm dyslexic with streets. I guess Elmwood should be over there. But in the other data layer, instead Delaware, they were shifted too far. So this dotted line is Delaware, that dotted line is Franklin, and that dotted line is Elmwood. So the second Franklin was actually closer to Elmwood than to Franklin. So the conflation process shifted all the streets one. And they were doing this to make sure bus drivers were driving down the right street for their route. And suddenly, one day they all got in trouble for driving down the wrong road, so they realized that the bus was on the right road, the street layer had them on the wrong road because they shifted every street in Buffalo over by one. That's a good example to tie into our discussion last week about error, too. And not every analysis works properly. So conflation is a GIS analysis. There are two major categories of queries or analyses, and we talked We've touched on this breakdown a couple other times in the class already, and we'll come back to that now. You have an attribute query and a spatial query. I think this is on there. This is a question I usually ask. Luckily, I don't remember. I wrote it a couple weeks ago, and I can't remember which questions I left on the test or took off, so I can't give away too much. An attribute query, but I usually, this is a question I would often ask is, one or two major categories of queries or describe the difference between an attribute and a spatial query, and it's an easy one. An attribute query analyzes features based on the attributes in the attribute table, where a spatial query analyzes features based on their spatial relationship to each other. So hopefully that distinguishes the difference, and we'll have some more examples of that in the next few slides. Here's an attribute query example taken from ArcMap. You'll find every Florida city with more than 100,000 residents. So I'm not really asking, other than the fact that it's in Florida, but we're assuming that I'm not asking about the locations of the Florida cities. I'm just asking to which ones have more than 100,000 people. So that's an attribute query. That's something I've done, like list queries and say indicate whether it's an attribute or a spatial query. And this would integrate attribute. But you could do that in Excel or Access. An attribute query is less unique to GIS. And that's another good way in your head to remember the difference. That helps for me. If you had an Access database of Florida cities or an Excel spreadsheet of Florida cities, you could build a filter in those tools to run this same query without GIS. An attribute query is more generic in the computer database world. So you understand how we're not involving anything spatial. It's just looking at the database and selecting cities based on an attribute, in this case their population. Note the difference of a spatial query. In the spatial query, we picked a particular county in Florida, I don't know what county it is. And we're saying which cities are within that county. So you see the difference immediately? It's a spatial question. We have a highlighted county. Right there, we want to know what cities are within it. So rather than looking at an attribute table, you're taking two layers. In this case, the two layers are the counties and the cities, and comparing them spatially. So this is the difference with a spatial query. One other thing, these type of queries only review data. We're not changing any data sets. We're just looking at existing data. Later this evening, we'll look at other types of queries and analyses that actually would change data. There's a minor point there on this slide too. But this series of the last three slides is actually a fairly important part of the class slide, is the attribute versus spatial query. That's something you'll see come up over and over. In fact, it already has, I said, in different parts of the course already. So those are some pretty important slides. Yes?
Can you talk more about the attribute theory and the complicated?
So with the attribute query, you ever seen the attribute tables in lab where there's information about features? In the attribute query, you're just querying based on a query you build on the attribute features. You're saying, cities greater than 100,000. You're not saying you're not querying, say, find cities near something or in something. You're basing the query on information from their table. So these cities, am I on the right side? These cities were selected because in their table, it's off the screen here, they have a population of greater than 100,000. So it's an attribute query because you queried it based on one of the columns in the attribute table. Does that help explain the difference? Good. You can certainly in one query or one query process combine them both. So this example, this is a two-step process in ArcMap to do it this way. But my question is find cities within 75 miles of Fort Myers that have a population greater than 100,000. So if you think about this question, incorporates a spatial component. What cities are within 75 miles of Fort Myers? And it has a attribute component. What cities are greater than 100,000? We'll talk about the difference between and or in just a few slides. So one query or one question could contain components of both attribute and spatial queries. We might also, okay. These are attribute and spatial queries that are dividing those two things again. But now we're changing the data in something called classification analysis. And we do this all the time in GIS or databases. So in classification analysis, it's an analysis of aggregating information based on an existing set of data. So for attribute aggregation, we're looking at a whole variety of different values and combining them into less categories. So you're taking a whole range of categories and combining them into less categories. I just thought of a perfect example. I will aggregate your grades at the end of the course. When someone may get 100, someone might get a 97.2, 95.5, and so on, 96.4. That may be grades of 4 students. What do? What do you get at the end of the class? You get a letter grade. You don't actually get the number grade on your UB report card. I'll make that available to you on UB Learns, but when you get your UB report card, you get A. If someone might get 86.1, and another student gets 84.2, 84.3. Those students will see the letter B on the report card. You understand how this is attribute aggregation? It's easier for the university to analyze how the student population is doing as a whole if we say 450 geography students got A's, 420 geography students got B's, versus trying to analyze the range of numbers. So this is attribute aggregation that directly applies to this class. Does that make sense? In GIS, I mean that's not really GIS, but we have often we'll get there's one like a chemical in the environmental consulting world, we'll do sampling. There's PCBs or some other thing in the environment that shouldn't be there. Unfortunately, there's way too much of that. And rather than report, sample. This sample is 4.5 parts per billion, 4.2 parts per billion. Often when presenting a figure to the public, these samples of parts per billion of PCBs might also be grouped into low, medium, and high. Or bad, good, moderate. So that's attribute aggregation. Spatial aggregation would be combining shapes that contain a similar attribute. You might aggregate towns into counties. I think I have a good slide here. This is Niagara County, just north of here. This is a GIS shape file of the zip codes. The Postal Service uses these zip codes to deliver mail. So the 14094 zip code covers Lockport and a lot of areas around Lockport. Niagara Falls has multiple zip codes and so on. So notice the zip code, I'm sure everyone knows that is a 5-digit number, but there is also, the colors, there's another classification of zip codes that's called an FSA code. It's just the first 3 digits. So you can see that the yellow zip codes are in the FSA area 140. The green zip codes are in 141. The blue zip codes are in 143, and that's more done for out-of-town mail. So someone in Boston wants to mail a letter to Lockport. The guy in Boston doesn't want to sit there and sort all the mail in different towns in Niagara County. They just want to get it here and let someone here sort through it. So the post office sorts it by the first 3 digits. If the first 3 digits are 140, it comes to Buffalo. And then here in Buffalo, they sort it out in individual zip code. So the post office uses spatial aggregation to simplify the delivery of mail across the country. Does that example make sense? It would be, if you took all the zip codes in Boston, if the guy there had that someone mailed a letter to, they'd have thousands of zip codes to sort through. It's easier to just get the mail to this general location, which would be Buffalo in our area, and then the guy in Buffalo just has to sort through the local zip codes and not the whole country. But when I'm sending mail, if people still send mail other than bill, I don't get mail anymore. It's a 20th century thing. But other than bills. How this relates to GIS is this spatial aggregation. Are there any questions? Now we'll go through a bunch of different one-off analyses, like I mentioned. They're all measurement analyses, each one's a little different. We'll talk about different types of GIS analysis. All ones that you would use. Some we've actually touched upon already in previous lectures. Some of this will be reviewed, some won't. Excuse me. So one of the simplest analyses in GIS, I mean we can do it right in Google Earth, is what's the distance between 2 points? What is the distance between, Tampa and Daytona Beach? I think that's Daytona Beach. So ArcMap has a measure tool, which you probably use, where you just measure between the 2 beaches, and it's 100-some miles. Pretty simple, but that's still a type of a spatial analysis. Think about it. Not very involved or complicated, but it is an analysis question we get all the time. I get calls from our geologist, how far is this well from this water source, or so on. Questions like that come up all the time. So just because it's simple doesn't mean it's not important. For that pipeline I keep talking about that's going to be built, or may be built in Pennsylvania, carrying natural gas, we need to help them report the distance from the pipeline to every potential water source and well and so on, because we don't want to contaminate people's water during the construction. We shouldn't want to. So they have to put that into a report and come up with an action plan to ensure the government that when they're building this, they're not going to contaminate anyone's water. But before they can do that, they need to know where the wells are. So Euclidean distance analysis from the potential pipeline to each well is critical in that location, in that situation. And I'm going to, oh, no I'm not, I found another slide. There's it's right on the same slide. This is a one-off measurement, but you can use also in this function called near, which is in our toolbox. And the near function is what I used in Pennsylvania, where you could relate one feature to another, to every single feature. So here I'm just measuring between 2 cities, but if I wanted to, so the question is, what is the difference from Tampa? What is the distance from Tampa to every Florida city? Rather than sitting there measuring every one, you would use the near function to do that. And it would add to the table for Tampa the distance to every one of the cities. That's the near function that uses Euclidean distance. And just to define Euclidean, it's a straight line. We're not talking about a network path. That's the next slide. In this type of Euclidean distance analysis, it says the crow flies. What's the shortest distance? However, that may not always work. So another type of analysis would be a network or a functional distance. We'll talk about this quite a bit more. I think it's actually the next time after the test. I don't think we have that in tonight's lecture. So in network and functional distance, instead of using a Euclidean or straight line distance, we look at across a functional network, which is usually a street network. Not always, but most of the time when we talk about this, we're talking about across streets. So if an incident occurs here, and we need to get a person from that location in San Francisco to a hospital, it doesn't do me any good to be Euclidean distance. You're not going to fly across the building to the hospital. And you might if it's Mercy Flight. But in this example, we're talking about an ambulance driving to the person, picking them up, and then taking them to the hospital. So in that case, what's more important than the straight line distance is what is the distance along the road network. how many miles is it, and more importantly, how many minutes is it. And we'll talk about network allocation later in the class, and I think it's April 14th. I'd have to look. So the difference between this, the biggest difference at this point to consider between this and utility distance is the network distance takes into account distance over a network. And a similar example here, this is a map from Arizona showing the areas that are estimated are accessible within 3 minutes from a fire station. Many municipalities have that in their code, that the entire city, town, whatever, should be within X number of minutes of a fire station for obvious reasons. And if they aren't, they build a new fire station. That has to evaluate network distance carefully and to evaluate what streets are accessible. I remember talking to a GIS analyst, I think it was in Mississippi, in Tennessee. They had a horrible situation in Tennessee. They had a house in between two train tracks, and it burned down because the fire truck couldn't get there because there were trains going by. And actually, it was one train track. Here's the house, train tracks, fire station. So you can see the problem, where they should have been served by a fire station on this side of the train track. So the house burned to the ground because the fire truck didn't get there in time. So the municipality did not properly analyze that using a network distance or network analysis. Any questions? We talked about this briefly with topology, but often I'm asked to calculate a centroid of a polygon. So a centroid is making a point of a polygon. And here's some examples here. It is usually the weighted center of the polygon, the center of gravity of the polygon. So if the polygon was a dinner tray, where would you put your finger for it to balance? For example, here, where'd the point go? I hit that good. The light comes down just the wrong angle, and I can't see this now. It's okay, it looks like that. So here, because I'm interested in these nerdy things, that's the geographic center of the 48 states. I'm sad to admit that I've been there. If I shouldn't come, but maybe that'll be the question. And I was sad enough to actually drive the application.
Where is that?
Lebanon, Kansas. That's it. That's going to be the question. We're not going to top that tonight. Lebanon, Kansas is the geographic center of the 48 states. There's a roadside monument. When you kind of visualize, it looks like it's kind of in the middle there. You see what the concept of centroid. North America? Rugby, North Dakota. I'm not going to add another one. Unfortunately, I've been here too. The center of North America is Rugby, North Dakota. They actually have a very big monument there. It's not really the center anymore. This is maybe a sad commentary side. They moved it across the street to build a mall. So the monument is actually across the street from the center of North America. The actual center of North America is now a shopping mall. Yeah, no problem there, right? So hopefully that'll stick in your memory what a centroid is. Sometimes, think about this shape. The centroid of the shape is actually outside of the shape. when you get an irregular shape like an L or a U. So in many programs where you're analyzing for a centroid, you can force the program to always pick a point inside, even if it isn't. If the weighted center is outside the point, you can force ArcGIS, for example, to pick a spot somewhere inside just to have it inside. But that's another quirk to think about with irregular shaped polygons, and it's not out of the question the weighted average would be outside of the actual polygon, like this example here on the right. Centroids, I think I showed a screenshot of this in relation to topology. Centroids are very important in property and parcel management. These are property parcels in Niagara County again. In most counties in New York State, I think it's every state, not just this state, when they maintain the polygon boundaries that are defined in the deed to your house. They also maintain the coordinates of the centroid. So you'll see that in your deed, or your parents' deed, or whoever owns the property. You'll see a description of the outline, a description of the polygon. You'll also see a description of the centroid. It might not use the word centroid, I don't remember if mine does. But that's what it's referring to, and it'll actually refer to that point with the coordinates. Are there any questions? Another one-off analysis would be sinuosity. And sinuosity is comparing the actual length of a line to the straight line from the start and stop point. And the shapes actually got shifted a little bit. They should, I don't know if I can fix that. I can. It should be like that. So what is the difference between the straight distance from a point to a point and the actual distance along the line? It's a ratio. So obviously the higher the ratio, the curvier the line. If it's 1 to 1, it's a straight road. And we'll think of this as a road. If it's 2 to 1, the road is traveled twice as far to get only half the distance, so it's pretty curvy. We're asked to do an analysis like this. Gosh, I might be going on 20 years ago. For a trucking company that unfortunately had some bad incidents in the Rocky Mountains, including fatality where the truck driver drove the big vehicle on a road that was too windy and curvy that shouldn't have been on, and the truck, in one case, drove off a cliff. So they did a sinuosity analysis to try to identify very curvy highways, and then put that into the vehicle navigation to prohibit the drivers from going on those highways. So there's a real-world example of sinuosity. Environmental scientists, hydrologists might also use it to analyze stream patterns. You know, if you have a meandering stream, it would have a very high sinuosity. There's another potential example. I haven't done anything like that, but I could see where someone might. Any questions? Okay, we're going to talk quite a bit about overlay tonight. This is a pretty important concept. The vector overlays, I think, are the most important, but not to diminish the rest of the discussion by any means. The vector overlays will be most likely to be on the quiz. So overlay, let's step back first and talk about overlay in a general sense. What do I mean by that? Overlay would be, it's just what it sounds like. Overlaying multiple layers to find an ideal location. You're looking for overlapping conditions. So it literally is an overlay. Before GIS and before computers, it was literally an overlay. They would have a map on a clear sheet of paper called a mylar with one feature. They'd have another mylar in the same scale with other features, and they would, when they said they would overlay, it was literally putting the maps on top of each other. Thank God we don't do that anymore. But that's where the term comes from. Yeah, I'm so sorry. We still have to do that. I guess we have to do that sometimes too. So here, A lot of times, especially in the environmental realm of GIS, we'll be using overlays to determine what we call either to rule out a site for a project or to find the ideal site. One example would be, we call it sometimes fatal flaw analysis. So if we want to build a factory somewhere in this square, a rectangle, and there's a bunch of different factors that go into this. We can't, maybe there's marshland, so it doesn't have the proper soil. The factory would sink into the mud. So if the marshland covers the left half here, I've ruled out that part of the rectangle. We can't build the factory there. We also, mom and dad don't like this kid's swing set next to a factory in the backyard. So let's rule out residential areas. So say down here, say this is a residential part of town. I've now ruled that out. And maybe here there's a school. It's not nice to have a big factory next to the playground either. Let's say there's I'm thinking my Hudson River project in eastern New York. Is anyone from like north of Albany? That area? No? There's a few. That's the biggest Superfund project in history. General Electric dumped a whole bunch of PCBs into the river over decades, and they're spending billions to clean it up. One of the things we help them do is find a spot. They need to get the PCBs out of the water, remove them from the water, which is literally called dewatering, and then take the sludge to some secret location to get rid of it. I don't know where. I don't want to know where it's going. Somewhere out of the state. I think they bury it in the same locations where they'll bury nuclear waste in Nevada and Utah, places like that. Because PCBs are pretty bad for you. For decades, you're not supposed to eat any fish from the river, which is really sad. It's a beautiful river. So that was when I first got into GIS at E&E. That was one of my first projects, over 10 years ago. So say, and I thought of this as was a problem. There's endangered bald eagles nesting near there, so you don't want to disrupt their habitat. Maybe the bald eagle habitat is here. So I've ruled out. If you see where I'm going with this, we're shrinking down the potential habitat areas. Let's say we want it to be near a major road. So if that's the major road, we want to be within 500 feet of the major road. We'll talk about buffer near the end of tonight. We've now narrowed down pretty much, so okay, you can only build there. That could be a fatal flaw analysis using overlays. And sometimes you're ruling out areas. If you don't want to build in an endangered species area, you don't want to build next to the school. But sometimes you're looking for areas that are positive. You do want to build near a railroad or a major road. In their case, there was a railroad going up the river and they wanted it right next to the railroad so they could take this contaminated sludge and get it out of Dodge as soon as possible. Like literally from the dewatering factory, put it right on the train and get it out. So that was a positive thing that they were searching for in that case, find sites that are near the railroad that goes through town. The first, I'm jumping around here. The first type of overlay that we'll talk about is a raster overlay. Raster data sets can be combined using arithmetic operations. And I think you have one lab, I can't remember if you've done that yet, using spatial analyst. You could do map calculator and spatial analyst to combine overlay using rasters. So instead of vectors, we have two rasters. Pretend they are on top of each other. I'll do an output over here. I'm way out of order tonight. So say these are the raster cells, and we are rating, we're looking for land to protect. And we're rating, let's say, does it have wetland? We want to protect wetlands more than any other feature. So in raster, we have a numeric value to represent. You have one value. Remember, most of you, I think everyone got that right, that question on the first test. So this is our wetland raster. And we have also endangered species, threatened endangered species. Sometimes you see TES. And in this case, so we're considering a high score good. In this case, the northern 2 pixels don't have much potential for endangered species. The most potential, maybe there's a nest there, is in this southeast corner. With wetland, with an overlay with raster, we would just overlay these pixels and add up the number. So you'd have 9, 7, 6, 9. So in the combined overlay of wetlands and endangered species, we've identified those pixels as having priority. Now maybe you'd have a tiebreaker, a third value. I actually did this something like this, not with the INI through volunteer effort for the Western New York Land Conservancy. I was on their board for a little while. They were working with Town of Clarence to identify, they had some grant money to protect habitat in sensitive areas within Town of Clarence. And we used an analysis like this to help prioritize for the town board which properties are not only most environmentally interesting, but most threatened. So if you have 2, that was the tiebreaker in this case. If you have 2 properties with an equally high value, this one's out in the middle of nowhere and probably fine. This one's adjacent to Main Transit Road, and there's a high risk of development. Developers want to put subdivisions in. That bumped the priority of this one up higher because there would be more risk of it being developed, and hence a more urgency for someone if their inclination was to protect it before it's developed. So there's a real world example that I volunteered on a couple of years ago of using a raster overlay. And then some other local towns have done similar things. East Aurora. I know there's others. I can't think of it at the moment. So that's a raster overlay. But to step back and summarize, the raster overlay is taking different rasters that overlay each other and adding up the pixels. And these would be scores of the suitability for whatever we're doing. When you add them up, you get a combined total. Here is a generalized set, and a vector overlay, we'll talk about it a little bit. We'll talk about some specific vector overlays near the end of tonight that are very important. And I'll guarantee they'll be on the test. And that'll be intersect, union, and clip. We're not there yet. We will be probably after break. But in the vector overlay, instead of a raster, I actually already sort of drew a vector overlay when I was drawing the Hudson River thing. But you have 2 shapes. So if this shape is a wetland, and you have a second shape that is prime farmland soil, and your initiative is, I would like to protect some land that is wetland and is prime farmland soil. See how you could use the 2 layers to identify your land? But in this case, these are vectors. You would vector overlay, and this is an intersect. We'll talk about this, the intersect, maybe an hour from now. With intersect, you would create a new polygon that's a vector overlay of the 2 polygons. So now we have our area that we know is both wetland and prime farmland. That makes sense? So that is a generic definition of a vector overlay. As I mentioned, we'll talk about some specific examples of specific definitions of vector overlays later tonight that are extremely important in GIS analysis, especially in environmental analysis like the examples I'm giving, but in all sorts of types of GIS analysis. It's something I'm probably safe to say our GIS department, someone in our group does something like this, I'm sure, every day. It's a GIS function. It's at the heart of what we use GIS for. Excuse me. And this is a kind of an abstract representation of what I just showed you. Here we have layer 1, which has 2 polygons named A and B. Layer 2 has 2 polygons named C and D. So this could be our wetland, non-wetland, where the wetland is A, E is outside wetland. Here perhaps D is the prime farm soil, C is not prime farm soil. And when we combine them, we get 6 new polygons, and the ones that are A and D are the area that are both prime and wetland. And in the new layer, it would be polygon J. And we crunch these. So again, this is also an intersect. Actually, this is a union. We'll explain that later. Any questions about this? Well, as I said, we'll go into more detail about this in a bit. What are the pros and cons? So obviously there's pros and cons to each, otherwise we wouldn't have both options. With rasters, a raster overlay is simple. If you think about it, I was simply adding up numbers. That's not very computationally intensive. You could do it manually. Versus vector, to run those operations, it takes more computer memory and algorithms to take those shapes and figure out where they overlap and where they don't. So a vector analysis is a more complex operation. Of course, things like that with today's computers become a little less of an issue because today's computers can do a lot of very complex things very quickly and efficiently, unlike in the past. The raster is simple. It's a simple operation. You get an answer for every single pixel. So if you want to analyze your entire work area, raster might be a way to go. Vector is often useful where you're only interested in a specific area. Like my example I gave where I said I'm only interested in areas with prime farm soil and wetland. That might be a case where you'd use a vector analysis because you're interested in intersecting these different layers to find a common theme where all of the different features come together. Vector overlay also lets you preserve attributes. If you remember, a raster only has the one number as an attribute. So if you need a lot of attributes to go with your analysis, you'll be doing vector. I'll tell you, usually a lot of these analyses that we talk about are vector-based. We do a lot more vector analysis than raster analysis. That may not be true for everyone, but that's been true in my experience, and I think in most people's experience. Are there any questions so far? So overlay also involves Boolean logic. So this goes into a philosophy class a little bit. I took a philosophy class on logic, which was pretty cool. We talked about things like this. This also will relate to that, where you have a query with more than 2 parameters, like I find cities within 70 miles of Fort Myers that are also more than 100,000 people. And the different types of analyses will be different types of Boolean logic. The first example would be an intersect. Keep that in your mind when we talk about intersect in a bit. Intersect is an AND query. With an AND query, both conditions must be met for the statement to be true. So in the here, and if the query is A and B, you're only looking at that area where they overlap. If I were to ask, is it cold and snowy? The only way you answer yes to that question is if it's cold and, that sounds obvious, is it cold and snowy? If it's cold like today but sunny out, the answer to the question is no. If it's snowy but This happens in Buffalo. If it's snowy but 40, the answer to the question is no. It has to be cold and snowy for the answer to the question to be yes. That's a typo. That should say or, not on. See the difference? That's a completely different question. Today I would answer yes, because it was pretty, I think it's a bit better than it has been, but it's still cold. It should be 49, I think. Is the normal high by now, and we haven't been really near that too much. So the answer to this question for today, actually I'll change that to no, because I don't think I was in Rochester for a bit, so I don't know, did it snow here? It didn't snow there. So good. Uh-oh. It snowed. There goes my hole. We'll pretend it didn't. It didn't snow there. I heard that it was snowing in some areas. We'll pretend that we'll talk about right now. Right now it's not snowing. So is it cold and snowy? No. Is it cold or snowy? Yes. And then the or condition on the chart, A or B, all of both circles get used. And that's called a union. Think about that when we talk about unions in a bit. When I also teach an ESRI certified class, and they make you take the class that the ESRI instructor gave another type of example that I will never forget. He asked us, because some of the students were confused a little about and versus or. He said, okay, how many of you are a male or a female? So if I were to ask you that, hopefully everyone that's paying attention will raise their hand. But everyone's a male or a female. How many people are male and a female? Use points if you raise your hand. Someone raised their hand next. It was in California. And it was a while back. So I think that was, I'll never forget that, because I think that was a good way to illustrate the difference between and or. If I say how many are male or and female, nobody raises their hand. Are you male and, did I say that right? Are you male or female? Everybody raises their hand, because you're either or. So that was a pretty good example too that the guy gave. This is more trivia than anything, but the Boolean logic statement XOR, only one of the conditions must be met for true. I wish I didn't erase that. I've never actually used this. So if this was, and it's not something you would ask very often. You don't go around asking your friends, was it cold, XOR, snowy today? If it's XOR, if it was cold, it would be true. If it was snowy, it would be true. But if both are true, it's false. If both are false, it's true. That's not on the test. Oh, this comes up sooner. Good. So that plays right into what I think of as some very critical slides. We spent, for that pipeline project, I spent almost the last year running intersection unions over and over and over. So I can explain why I talk about this. So these are specific vector operations. There will be questions on the test where what I might do is ask you to union certain shapes, what would the result be, or intersect certain shapes. This is union. We'll talk about intersect. I think it's the very next slide. Yeah, it is. And both of these are very important in GIS. So with union, it's like the or from the previous slide. You cookie cutter the two layers, but you still preserve all of the areas, not just the areas that overlap. So I have an example here. I'll draw it too, because that might be a little confusing. Now I wish I had, this is even easier with two color markers, and I only have the one marker. So let's say these are counties. And we have A, which is Erie. B is Genesee. And we have, I don't know. watershed. 18 Mile Creek water. This is, I'll make 2 watersheds. And I'm purposely not making them over the whole area. 18 Mile Creek watershed. This is probably not factual. I'm making this up. And Owaka Creek watershed, which is the number 2. If I were to union, so I've started out with 4 features. I've got 2 counties and 2 watersheds. If I do a union, they are cookie cut, they're overlaid, but all of the existing features are preserved. Here's where I really do wish I had another colored marker. I forgot about this. It's more complicated than I wanted to. So here now we have 1, 2, 3, 4, 5, 6, 7 shapes, where we had 4 originally. And this is a new layer that's been unioned. And so this is A dash nothing, because there's no watershed there. There is, but there's not in my layer. So it'd just be Erie. All of the attributes from both layers come over with a union into the, to just reiterate, we're taking 2 layers, counties and watersheds, unioning them. We're making a 3rd brand new layer. We might call it counties dash watershed or something like that. This one is B dash nothing because it's Genesee, but it's not in a watershed. This shape would be A dash 1 Erie 18 Mile Creek. This would be nothing dash 1 because it's not in a county, but it's 18 Mile Creek. B dash 1 because it's Genesee 18 Mile Creek. B dash 2 Genesee Owaka Creek. Here we have nothing dash 2 because it's Owaka Creek, not in a county. And in that little sliver there, it's nothing dash 18 Mile Creek. You see how we've split at every boundary of the 2 layers and come up, we've taken the original 4 shapes and made 7. Just like they've done here. But the key in union, and we'll see how intersect is different in just a moment. So here's our new number 1, new number 2, 4, 5, 6. Actually, there's 8 shapes out of 4. The key is all original shapes are still there, even if they're only in one of the 2 layers. Like even though this is just Erie County, there's no watershed, that shape remains in the union after the union when we create the brand new layer. So we have this layer with the 5 squares in it, this layer and the 3 circles. They've done something similar here and created 15 different shapes. And another key point is the new layer. I mentioned this before, but just to review, the new layer has all of the attributes of both of the original layers. And I don't want to overcomplicate this. So the simplest example is 2 original layers, but it doesn't have. It could be more than 2. You could have as many layers as you want. To describe this, I think it's easier to think of it to start as 2 layers. Here is. This might be a little simpler. I copied this from ESRI's help. Here's an example from their help on union of taking this purple layer and this yellow layer and unioning them. They're split up, and again, the output contains all of the original shapes. And the reason I keep mentioning that is the next analysis, which is probably the most. If you made me ask what analysis of all these do you use more than anything, I'd probably pick this one, intersect. That might vary. I mean, we said we are an environmental company, So we're doing a lot of things using intersect, and others might not answer the same way, but I would say of all these analyses, the one in my career that I've used more than anything is intersect. So the difference with intersect is only the overlapping areas remain. So we're taking 2 layers or more, we'll start with 2, intersecting to a brand new layer, just like we did a minute ago. But the fundamental difference between union and intersect is only the overlapping layers remain. So the intersect layer is going to look very different. The intersect layer will look like this. The intersect layer will have only 3 shapes in it, because only these southern areas of the county that have a watershed and this eastern edge of Genesee County, those are the only areas that will remain because they're the only ones that overlap. They're going to understand the important difference between the two. But just like union, what it has in common with union is that it also has attributes from both layers. So here's my sketch, and this is what intersect would look like. It's not out of the question that I might have some abstract shapes like this on a test and ask you to draw what they would look like after an intersect. There's a good chance of something like that, because I think it's so important. So here in this case, in their example, only again over the overlapping areas show up. And here is, I also copied ESRI's help for your benefit here. And they also show the intersecting of the 2 layers, again leaves only the areas where they overlap. Are there any questions on union and intersect? Does that make sense? Clip is similar to intersect, but with a clip operation is more of a cookie cutter, where you're using a polygon to extract a subset of features. So if we have roads, those are the entire town's roads, and I am interested in just a specific area. I'm not interested in any attributes from clip. Unlike union and intersect, when you clip, you're just extracting information from one layer, and the output will only contain the attributes from that layer. So if this is a clip, and I provide this polygon, it's like, I used an example of cookie cutter. That would have been bringing cookie dough if I have cookies tonight. So I'm hungry again. You put out cookie dough, and then for Christmas cookies, you take the cutter, and then you cut the dough at that location, and then you extract it, and you have just the shape of the cookie. That's really what you're doing here, but not with a cookie, in the GIS world. So when we clip using this polygon, you would get that result. You would get only the roads within the polygon. If a road goes outside the polygon, it would cut the road at that location. Yeah.
That's similar to like cropping.
Cropping is a very good example. Like in an image, you could probably call it the same thing. Only in GIS we call it clip. In Photoshop, a lot of our tools do call it cropping. That's an excellent comparison. But another key thing about this is the attributes of this polygon are irrelevant. We're only using its shape to crop or cut these roads out. We'll do this the water department does it all the time. They have water mains for the whole county, a contractor will call because they're reconstructing a main, on Frontier in Skinnerville. They don't need the water mains in the whole county. They just want a map of the mains in that project area. So they'll send a polygon and say, can you clip your data to this polygon because I'm only interested in my study area. That's a good use case for clip. And another pretty common one. Any questions? And there is ESRI's clip. And they're kind of mentioning the same thing that I talked about. They even call it cookie cutter. Not just me. They're also kind of giving a similar example where they say it's particularly useful creating a new feature class for your area of interest. So if you have a larger feature class, your area of interest for your project is just this circle, clip out the layers just to your circle, because anything outside the circle you don't care about. Your area of interest is smaller than the layer. Make sense? The opposite of clip is an erase. So if we have, with erase, instead of extract it, you provide the polygon. With erase, it removes the street from that polygon and leaves everything else. This is going to be easier to do it this way. Eraser is a good tool to demonstrate erase, I guess. So I've used the eraser to demonstrate. So with erase, I use a polygon, run the erase command, and the features inside the polygon are gone. Questions? So they, especially clip, union, and intersect are pretty critical. Like I said, those are commonly used GIS analyses. Another type of analysis would be a spatial join. Spatial join is the name of the analysis right in ArcMap. You join attributes from a join layer to another layer based on a defined spatial relationship between them. And then you create a brand new layer containing the data from both. So if you have a county layer, it has Erie County, New York, county seat Buffalo. And we have another layer of SUNY institutions. We only know that it's UB. We have Geneseo there, SUNY Geneseo. Or we could even have Chautauqua County, SUNY Fredonia. The question may be, in our shapefile of SUNY institutions, only has the name of the school, and we may want to ask, what county is each SUNY school in? We could perform something called a point in polygon spatial join. This will create an output, a new layer, and if the spatial join, if the target is points, the spatial join will look at, you have a target and a source layer in a spatial join. It'll look at the polygon it falls within pick all of the attributes from that polygon and attach it to the points. So now in the new layer, UB would also have attributes that say Erie, New York, Buffalo, Fredonia, would say Chautauqua County, and so on. Geneseo would say Livingston. So it's a way to combine attributes from two different layers. It's kind of a conflation in a way, to get two sets of attributes on one layer. So in this example, here's my zip codes of Niagara County again, and I have a point vector feature class of schools. And the question is, I want to know what zip code every school is within. Say the school shapefile doesn't contain zip codes. Here's our toolbox spatial join, where we're joining zip code attributes to the target layer of schools. And now here's our result. It creates a brand new layer, schools, zip code spatial join. And when I identify in ArcMap a school in this new layer, now we see both sets of attributes. We see W.H. Stevenson Elementary School. We also see the zip code that it's at 14131. So again, the spatial join is the combining of attributes based on the spatial relationship. And point in polygon, like I've done here, is usually what that's used for. Any questions on that? Another commonly used analysis is buffer. Buffer creates a new polygon layer that represents all areas within a certain distance. So the source could be a point, line, or polygon. So if we're starting with point, and we create a buffer of 1 mile, the new layer would have a circle around every point with a radius of 1 mile, like shown here. The input data could be a line that you're buffering. And this is a real-world example. This is a train track that carries trains with hazardous material. You want to know everything that's within a half a mile if there's an incident. Unfortunately, it happens too often. It was a pretty bad one in Quebec a couple months ago carrying oil. So buffering the train track by 500 feet, for example, will give you 1,000 feet, 500 on each side, gives you a polygon. You can also buffer a polygon and make another polygon. And what is within 10 miles of Erie County? So you're starting with a polygon, you might create a new shape that's Erie County expanded 10 miles. One unfortunate example of where we used point buffers for Niagara County was for the probation and police department. They have a regulation for registered sex offenders that they can't, once they've been convicted, they can't live or work within 1,000 feet of a school, playground, park, or anywhere else where children might congregate, like Chuck E. Cheese or something like that. So they have a point layer of all those such places in Niagara County, where a Chuck E. Cheese or daycare center, schools, parks, and they buffer each point by 1,000 feet. So they have a layer that looks like this. So when this individual comes into the probation department and says, I want to move to this location, I have a potential job in this location, if it falls within that, they say no. There's an example where we helped them out with this, it's an unfortunate example, but yet a valid example of using point buffers in a real world example. I think, I can't remember exactly how I asked if there's a question about buffering, I'm sure. And one key thing to remember is regardless of the source shape, whether it's a point line or a polygon, it always ends up a polygon in all three cases. And speaking of unfortunate examples, point buffers are often bad. This actually happened 4 years ago. Was it that long ago? Wow. I actually was doing this lecture that in March, I think it was 2012, 3 years ago, March 11th, 2012, there was the tsunami, earthquake, and then the horrible tsunami in Japan. And I found this example of the tsunami and earthquake was one thing. If you recall, the nuclear reactor in town was damaged, causing a radiological hazard. So I found this on CNN the day of the lecture. I was giving a lecture in March of that year, where there was a series of point buffers around the Fukushima nuclear reactor, where they were recommending evacuations. And I remember it was interesting that the U.S. government actually recommended a larger buffer than the Japanese government, where they had said, everyone within 20 kilometers of that nuclear reactor should be gone. It's not safe to be there at all. Within 30 kilometers, they didn't want planes flying over it. They wanted everyone there indoors. I think that's good enough for me to leave. I'm not going to stay inside. I remember it was in the news that the U.S. government actually felt it was the worst danger and had recommended to U.S. citizens that were living in Japan that if they were within 80 kilometers, that they recommend that they leave. But it's an example, another unfortunate example of a use of a point buffer. And the other key point that I like is not that I like about the slide, but the slide map demonstrated effectively is sometimes you need multiple rings, and that is an option in ArcGIS. In this case, we don't just have the 20-kilometer zone, but there was a 20-kilometer total evacuation, there was a 30-kilometer stay indoors, and an 80-kilometer zone where the U.S. government asked American citizens to vacate. So that's a multiple ring buffer. In the previous examples I gave, didn't incorporate that. In the sex offender case, it was just 1,000 feet straight up. But in this case, there were multiple scenarios, so we have a multiple ring buffer. And here's another multiple ring buffer as a scheme that I don't remember the point of that, other than to show that you could also multiple ring buffer on streams as well. Any questions? One, not too concerned about this, but point and polygon analysis, kind of like spatial join. Take a series of points and analyze it to see whether it's within a polygon or not. We'll talk about some topographic analyses now. It's not quite 8 yet. We don't have too many slides. If it's okay with everyone, rather than do a break and come back and do lecture, we could plow through the slides, take the break, and come back and do the exam review. Does that work for everyone? I thought it was okay. There's a few more, but not too many left. And I usually like to break around 8. Okay. It's long until Tuesday night. So we'll talk about some raster and other vector analyses that are analyzing topography, elevation, so on now, if there's no questions. And some of this is review. Some I mentioned, I remember mentioning even last week. Elevation, we've talked about this multiple times. And simply, what was depicted here is a DEM, digital elevation model, showing change in elevation. But we can run analysis on a DEM and provide these two additional rasters that show us aspect and slope. I'm sure I did mention these, and now we'll go into more detail. Aspect is an analysis that indicates the direction, the compass direction that land is facing. So if you're on the north side of a mountain, your aspect is north. So you can obviously, if you think about digital elevation being terrain modeling, if it's not flat, and you see I don't see anything here, that's hard to read. The gray area indicates that you're on a flat surface. If the land is flat, there's no aspect. But say the chair is facing, the aspect is west, I think, or east. I think that's west. So now the aspect of the chair is east because it's facing that way. And here in this screenshot, west would be the areas that are blue, east are the areas that are east. Yellow are the areas that are east. Now I'm going to have to, because it's 2015, there's an app for that. And it's not a compass like everything else, it's on a phone. The phones used to be for talking. Well, I'm way off. I lose points on the test. Is that right? That's northeast? Boy, you couldn't be. It's just about as wrong as you can get. Maybe I'll give everyone a point. That's actually northeast that way, but you get the point of aspect. Aspect actually doesn't. It sounds trivial, but it's not. Hiking and wayfinding, it's important. But even in agriculture, even in the same climate zone, the same area, the slope of the land could lead to a very different microclimate. And I just thought of this. I was in Rochester for my daughter's doctor's appointment this morning. And if anyone here is from east of here, and you drive back to Buffalo on I-90, just before you get to Batavia, you go over the escarpment, and there's a area that faces east, kind of southeast, which is away from the sun in the winter. And there's always snow there. It's always the last spot where you see snow. Next time if you're coming from Rochester or Syracuse, look for that. I noticed today, even though thankfully most of our snow is melted, at this spot near Batavia where the aspect is southeast, there's a lot of snow there still. It looks like there's still a couple feet of snow because the aspect of that particular stretch of land is southeast and it never gets the sun. It doesn't help that it's treed either, so there's shade. So that is a local microclimate because of the aspect. And if I were to plant crops on that stretch of land, I might plant very different crops than I would on a northwest facing property which gets a lot of sun in the winter. So aspect can actually be very important in that example in agriculture. And it affects the hydrology of that land too, because that snow not melting, I've seen it in May even, probably means that land is wetter because it's not getting a chance to dry out as soon because of the aspect. Closely related to aspect is slope, where aspect is an actual direction. Here now I'll get it right, the chair is facing northeast. The slope is the percent where the chair is at 40, the slope would be 45 degrees or 10 degrees and so on. So slope is the actual percent, height over width, where aspect is the compass direction. So that's sometimes a good test question, describing the difference between aspect and slope, because they're both elevation analyses. Does everyone understand? And here's another slide showing, again, broken down by direction, and then the percentage using grass. And that's still around. That was an open source GIS program. It used to be heavily used. Any questions? A few more slides actually will build upon the first lecture after the exam. This is more of a general introduction to a major topic of spatial interpolation. And spatial interpolation, so we're shifting gears a little bit. It's still an analysis, but this is a different type of analysis. And spatial interpolation answers this question. How do I predict geographic information about areas for which I have no data based on data collected nearby? So if and I'd like to use weather for this, can I predict, there's a weather station in Lockport and a weather station in Buffalo, and they have temperature readings. Can I use, and maybe there's other weather stations, one in Niagara Falls maybe, I know there is, one in Batavia. And let's say someone calls up, your grandparents call, so they're coming back into town. They're coming to Pendleton. They want to know what the temperature is. So they call you up tonight and say, we got a hotel. They live in Pendleton. They're visiting family in Pendleton. They're coming up from Florida. What's the temperature? Are you going to say to them, I don't know the temperature in Pendleton. There's no weather station there. You would probably look at the news and get the Buffalo temperature, right? Say, well, it's around 39. Well, that would be it. When you answer it that way, you're interpolating. You don't really know the exact temperature here, but you're using nearby data to guess. You can't, at least as of now, with the way technology is going, maybe you can't possibly survey the temperature at every single location. So you need to make an educated guess in that sense of what the temperature is in this spot, because we don't have a weather station, but we have nearby data. We do this all the time for environmental GIS and sampling for pollution. There's also quite a bit of, unfortunately, bad things at the bottom of the Buffalo River. Buffalo River is very contaminated, sadly. It's another nice river. So we were part of a multi-team project that did sediment sampling in the Buffalo River a couple years ago. That's another case where you can't remove the whole river and sample the entire river. So you sample certain key points. And that's a GIS person's job, but it's also a statistician and a geologist's job as well, is to pick the points. Okay, if I pick core samples here, and it's kind of cool. I helped plan for it. I've never seen it done. It would be kind of cool. They have a metal core that they drill down into the sediment, the river, close it, and then bring the dirt back up. It's really cool. I have to take other people's word for it. I haven't actually seen it. And then they bring that core of sediment back into a lab to test. So there's a lot of science that's not just GIS in picking those points, because you can't sample every single location. So you're picking locations that are representative of the whole river. And that's a whole science unto itself, and that's spatial interpolation. Even another example of interpolation that's not spatial is election polling. Before a presidential election, they don't contact every single American and ask them who they're going to vote for. They contact the 1,000 or 2,000 Americans that they think are a representative sample of the entire country. And it's amazing, especially the last couple election cycles, how close they get. I mean, they're picking election results pretty accurately. There were some people saying that the elections were rigged or skewed before the last election, and as it turned out, the polls were dead on accurate. And the presidential election turned out exactly as predicted. So that's not spatial interpolation, but that's still interpolation. So how do we guess? How do we guess about features where we don't have data based on nearby data? And we'll talk a little bit about that now, and then pick that up in more detail after the test. And in the simplest example is linear spatial interpolation. There's a linear relationship between values. So here's our sample point. We don't know the amount of PCB at this point. And there's 10 parts per million here, 20 here. With linear spatial interpolation, we'll guess, oh, it's 15. There's a linear relationship. Something that's twice as far has half the influence on our decision. If you're interested in the temperature in Pendleton, the Buffalo Airport's 10 miles away. The Batavia Airport's 20 miles away. You're half as interested in the temperature in the Batavia Airport as you are as the Buffalo Airport, because it's 2 times as far. We'll look at non-spatial, non-linear interpolation. I don't think tonight. I think one of the first things we'll do in April, if I remember right. So here is a raster that was run. So again, to define linear spatial interpolation, values between known data points are filled in on a linear basis. There's a linear relationship between distance and value. If something's twice as far, it has half the impact. So here's taking points. These are points of city locations with their populations and predicting population density in between the cities. And just from this, you can kind of maybe get an idea where this would be flawed, because you're assuming that the phenomenon, in this case population, is evenly spread out. In that case, we know it wouldn't. So often this doesn't do the job. If you think about it, things are not that neat in nature usually. So after the text, we'll talk about other more complex interpolations that usually are used instead of a linear analysis. But we're starting simple. Okay, now. Another spatial interpolation is called a Thiessen polygon, or an area of influence polygon. So given a point layer, each Thiessen polygon is the area that's closer to that point than any other point. So if I have this blue dot, that polygon associated with it, everything within that polygon is closer to this blue dot than any other dot. Everything within this polygon is closer to that red dot than any other dot. And they're created using perpendicular bisectors between lines connecting the points. I'll think I'm going to ask that. Using a process called Delaney triangulation. I can try this. Sometimes it goes wrong. If we have a couple of points here. To create these in polygons. You create these in polygons in ArcGIS, you have to use a tool to do it. It'll do it for you. But if we had to do it by hand, you draw lines between every dot, and then you draw perpendicular bisectors cutting the lines in half. That cuts that line in half. I like that there's a tool that just does it. So now if I erase in between these lines, I think I did all the lines, that's okay. Now this is the Thiessen polygon for that point. This is the Thiessen polygon for this point, and so on. And that's called Delaney triangulation. But the most important point is that the Thiessen polygon represents an area, all the area in space that is closer to that point than any other point. And this is kind of a simplistic way to analyze this question, but I found this report done in North Carolina in 1989 where they were concerned there wasn't enough OB/GYN child service in the state. So they used these in polygons to determine region boundaries where they needed to add more such hospitals. So the hospitals that are centers for this need are located in these Asheville, Charlotte, Salem, and so on. And the dark black lines are these and polygons between those points. Here's another case of elevation modeling using these and polygons. In this case, we have points where elevation's been recorded, and we created a Thiessen polygon around each of these elevation points to create an elevation model. We'll talk about IDW and then we'll finish. IDW is a more complex and more used spatial interpolation than linear. In IDW stands for inverse distance weighting. So this commonly used method takes neighboring samples into account. It makes the assumption that the further away the known sample is, the less effect it has. So if we're wondering about this point, what's the value here? And we have a known point here and a known point here. This point, it seems logical, doesn't it? This point will influence our answer more than that point. And you might say that's not always, we'll talk about this, I don't think, it'll be one of the last slides here. There might be barriers. I mean, there might be a barrier here where actually this point does influence it more. And if that's the case, IDW doesn't work necessarily. And in the simplest case, if, I'm not doing real math, if this value is 100 and that value is 50, our IDW weighted prediction for this point is going to be closer to 100 than 50. It might be 87, something like that. Here's an example. Here's the same elevation surface using the IDW method. But the key slide is the next one. What's very important with IDW is you can increase the power. So as you increase the power, the effect diminishes more quickly. But they're 150 at a, and I don't think you would ever actually do this, but if you set a power or a P as 0, we're saying distance has no effect on our calculation. And we might say 75. We split it in half because at 0, I am uninterested in the difference in distance between those 2 points. So an extreme example, if we're asking about Pendleton, we'll weight the temperature in Buffalo and the temperature in Boston equally, or New York City, even though the distance is greater. You can see where that usually isn't done. Let's say this is 1 mile, and that's 4 miles. At a P of 1, this is linear interpolation, like we talked about earlier. There's a linear effect. So here, it says 5 miles total, so you'd be 4/5 of the way. See, this math is getting good. So there would be 4/5, the value would be 4/5 of the distance between 100 and 50. I'm going to make this 2. So this point will be weighted twice as much. Which might be 87. Instead of 75, it's going to, this point will be weighted halfway between 75 and 100. if a p, so because it's linear, we're saying this point has twice as much influence on the value because it's half the distance. At a p of 2, which is the default, I think, there is a exponential relationship to the second power. So this would have 4 times as much weight because it's half the distance. So it might be 92.5. So the closer the known point gets, it has a more disproportionate effect because the relationship is exponential. And what is the right? I can't answer that question. You might have a subject matter expert. If it's pollution, you would bring in a chemist or a geologist to say, this is how this pollutant disperses. They might be able to tell you this more than a GIS person could. If this were 3, something half the distance would have 8 times as much effect. I had to write it out because it's 2 to the 3rd power. That makes sense. So something is half the distance. It's 2 times closer. At a p of 3, it would have 8 times as much power, just by being half as close. At a p of 4, it would have 16 times as much power. So as p increases, the effect of further points drop off very quickly. So if you think about that, let's say p is 4. This point, just by being halfway the distance, will have 16 times as much effect on the value. So it could be something like 98. And anything higher than 4 effectively renders this one inconsequential, if you think about it, with a higher p. Whereas the other extreme is at a p of 0, they both have equal weight. The most important thing here is the relationship of this p-value and how raising the p-value diminishes the effect exponentially of further points. Does everyone understand that? I think that's the key in all this, all the words and text here. I think that's the key. That's the most important thing to take away from this. And the graph shows here, at p of 0, distance has no effect. There's still a complete influence. But notice how the curve goes down to 0 quicker with the higher p. So here we're almost at a 0 effect, much quicker than we are at a p of 1. That's the key of IDW, is this power. And again, there's no right answer. The default is 2, I think, if they haven't changed that. A geologist or an expert would have to help. Often in that case, it would be an expert telling the GIS person, hey, use this power. So here's source data of contours. So if you want to predict values at certain locations from contours, here's how the results are quite different based on a different power. Not to worry about that. And then on the last slide, you can control, I mentioned this could be a problem, you can control neighborhoods in IDW. And here's some settings that you could also bring into effect. You can set a maximum distance. So these are other IDW settings that are available. If your maximum distance is 1.5 miles, you can cut that off and say, I don't care. Any point beyond the maximum distance will not be included, irregardless. P or no P. In variable radius in IDW, that actually changes the game quite a bit. Instead of the closest one, you would pick, say, the 3 closest points. And then just analyze those, even if the 3rd point is far away. In a fixed radius, it's actually similar to a maximum distance, and maybe the same. I have to think about that. You would only look at points within a certain distance. I think that is really, really the same thing if you think about it, exactly the distance. And you can use a line feature to deploy barriers. And that's very important in geology. Because if this is the dispersion of a pollutant, so this point's really close. There might be a geologic barrier there. And in reality, this point influences the value here. Especially, okay, say the flow is this way. even though this point is super close, if there's a barrier bedrock and the flow is this way, the value at this point might be more affected by there than here. So you can use a line file of barriers. We did that for a project. This San Gabriel Valley is near LA. There's a lot of groundwater contamination. They know the sources, but there's some locations very close to the source that have zero pollution. And it's because of geologic barriers of bedrock that are blocking those areas from getting any of the pollution. Yep. Yes?
Are there a percent valuable barriers? Or is it an all or nothing?
I think it's all. I'm going to say all or nothing, but there's got to be a way. I've never done that, but obviously there would be cases where you would want to. I would think you could do some of that with a raster where you're indicating a higher impedance. You might not use this method. That's how I would do that, but I think the barriers, I might be wrong, are all or nothing. But you could use an impedance raster to get at what you're suggesting, I think. Any questions? So that is the last slide. I'll stop the